Okay, so let's continue our discussion about return contracts. So I will first do the derivations we need and then use the derived results to give you some insights. Afterwards, we will have some final remarks. Okay, so what we have done is to told you that the expected system profit is can be derived in this way. Actually, this is nothing but a news vendor problem. Okay, so the system optimal inventory level, we're going to call it QT star, satisfies this equation, which is the usual news vendor formula. Okay, we hope that there is a return contract with the three parameters W, R, and capital R that can make the retailer orders QT of star. Okay, given the parameters C and P, we know what should be the QT star, and we hope the return contract can induce the retailer to order this quantity. According to what we have done in our last lecture, we know under the return contract, the retailer's expected profit is this thing. Okay? Yeah, there we spend a lot of time to derive this result, and here we're going to depend upon that to find the retailer's ordering strategy. Okay, certainly the retailer would make an order decision to maximize his expected profit. So let's ask, how will he do that? And certainly one thing we need to do is to do a differentiation. So how? This is a function of Q. The Q is here, Q is here, Q is here, here, and here. Q is everywhere. So here, when we want to do the differentiation, we need to apply something you learned in calculus. This is something we called the Leibniz integration or integral rule. Okay, so let me make a brief explanation. Suppose there is a function f. F is at least a two-variable function. Suppose f can be differentiated over y, and this partial derivative exists and is continuous. Okay, some regular condition we need. Then what we have is here. Suppose f has been integrated over x. The lower bound and upper bound may be some function of y. Then we know this thing here, after this integration, this is only a function of y. And then you take the first order derivative of that function over y. Okay, this is something we want to do. And you may observe that this is exactly what we need to deal with the retailer's ordering strategy. Here, the y would be our q here. I want to differentiate this function over q, and this function is found by an integration over x. There are so many x here. When I want to do this differentiation, I see there are something inside the integration that contains q. At the lower bound or upper bound, there are something contains q, and I want to apply this general formula to my retailer's problem. So I can see after the differentiation, there will be three parts. The first part is that here, you need to plug in your upper bound into your integral. Okay? And after you do this plug in, you just need to take the upper bound and do a differentiation with respect to y. This is some kind of chain rule. And then you do the same thing to the lower bound. You plug in lower bound into the function here, but now the coefficient would be negative. And then again, you need to differentiate the lower bound, put it here. And then finally, you're going to take this part into the integral. Okay, you're going to take do the differentiation here. After you do the integration, after you do the differentiation, you do the original integration. Okay, so the Leibniz integral rule is telling us how to deal with this kind of situation, how to solve the differentiation of pi r of q. So that's certainly something complicated, and we need to do that, whatever. Okay, so I list the Leibniz integral rule here for you to do a reference. And we're going to do this integration and to do the differentiation. At the left-hand side of this table, I list the 4 components of the retailer's expected profit. Okay, and to find the first-order derivative, we need to do the differentiation one by one. For the first component is the easiest. Differentiating this over Q, we get this negative W. For the second part, we need to use the rule. We know there is an upper bound which is a function of Q. In this case, the first term, we need to first plug in this upper bound into the function, the integral. Plug in that into those x parts. That's how we get this. Okay? And then we need to differentiate the upper bound by Q and then do a multiplication. This is how we get this guy. After that, for the second term, because this is not a function of Q, so after in the differentiation it becomes 0. We don't need to worry about that. And finally, for the last part, we need to take the differentiation inside. So that's why the lower bound and upper bound is still there. We still need to do an integration, but now we have only capital R times small r times f of x, because after the differentiation, Q will disappear, and actually the first part will disappear. Okay, that's how we do for the second term here. And you may want to verify that you can do so for the third term and for the last term. You will get the results here. Okay, so after you do all of that, you may verify or you may do some more calculations to show that all those terms regarding the PDF, the small f term, will disappear, and all you will have is these things remaining, and all these integrations are now can be expressed by those capital F, those CDF functions. After you do all these derivations, you will get something here. Okay, there are two constants, negative W plus P, and there is something related to the capital F of Q. These are all something you may have when you have a usual Nussbender problem. But now you have something more. Because you have this return policy, here you have a term regarding capital F as a function of 1 minus R times Q. This depends on the amount of quantity you may return to the manufacturer. Okay, so now the question is, given a contract W, R, and capital R, the retailer needs to find a quantity QR star to make the first order condition satisfied, to make the first order derivative equal to 0. Okay, you may want to verify that if you do the differentiation again, you will get the second order derivative, and that's going to be non-positive. Okay, and that's how this function is concave. Okay, anyway, as you can see, it's hard to write down a closed form expression for the optimal QR star, but at least a numerical search will be enough for us to find the number for a QR star, given all those contract parameters, given all those outside parameters. Okay, one question you may want to ask is whether this equality can always be solved with a unique root. Okay, how do you know there is indeed a QR star that is reasonable and can really solve this equation? How do you know if there is one root, there is no other roots? Okay, that's something you may need to answer, and I'm going to leave that to you for you to think about that, and we're going to discuss that in class. Okay, so let's continue. Now the question is, how may we induce the system optimal inventory level? Let's say that again. So the system optimal inventory level is called QT star. It must satisfy this equality. Okay, and now if we want to induce the retailer to order this quantity, the system optimal quantity, we need to make Qt star an optimal solution to the retailer's problem. And that means if we plug in Qt star into the first order derivative, we must get 0. Otherwise, Qt star will not make the retailer optimal, and the retailer will never choose Qt star. Okay, so we need to plug in Qt star into the first order derivative of pi r. And if you do that, this becomes Qt star, this becomes Qt star. And one thing we may say immediately is that this part, f of Qt star, is something we know. It must be p minus c over p, p minus c over p here. Okay, that's how you get this second equality, and we know it must be 0. So to achieve coordination, we need to choose a contract. We need to decide 3 values, W, R, and capital R, to make this equality or equation true. Okay? And we know Qt star is something defined according to this expression. So now the problem is precise. We know Qt star is fixed according to P and C. Okay? Qt star is fixed. And then we want to ask whether it is possible to find W, R, and capital R to make this equality true. We want to answer whether it is possible. So now, given all those analyses, now that's going to get the final conclusions of this paper. We call them insights, and later you will see why do we say they are insights. So let's consider the first extreme case. The first extreme case is that we're going to be the most generous situation. Let's assume the manufacturer is going to offer 4 returns with 4 credits. Okay, let's see in this case whether it is possible to make the retailer ordering Qt star. Okay, we have this proposition. Suppose R is W, this means 4 credits, and the capital R is 1, this means 4 return. In that case, the condition, the first order condition can be true if and only if C is 0. Let's see how may we prove this. Suppose R is W and the capital R is 1. Then the desired equality will become this. Why? When R is 1, you know this part is cancelled. The whole term here will be cancelled. And then your small r becomes W, and that's why this part becomes this part. Okay? And then you may take P minus W outside, you're going to get this. You know P must be greater than W. Your retail price is greater than your wholesale price. And that's why this part can be cancelled. It cannot be 0. So all you may have is for the last part to be 0, and that requires C to be 0. So if C is 0, yeah, this can be true. But if C is not 0, it's impossible for this to be true. Okay, that's the concept here. So mathematically we showed that. What's the interpretation of that? Well, what we learned from that proposition, from that theorem, from those mathematical derivations is that if the manufacturer allows 4 returns with 4 credits, then the system would generally be suboptimal. That means the retailer would generally not choosing the system optimal quantity. The condition we need is for the C to be 0, which means for the production cost to be 0. We know in general this is not true, right? So that means this condition cannot be satisfied. 4 returns and 4 credits somehow intuitively is too generous, and the retailer will not be induced to choose the system optimal quantity. Okay, so let's consider another extreme case which we have actually investigated. Is the no return situation. That means I am just offering a wholesale price contract. That's proof wholesale price contract can never be coordinating. So this is also the least generous return contract. The proposition is here. If small r is 0 or capital R is 0, which means there's no return allowed. In that case, there's a typo here. The required first order condition cannot be satisfied. Okay? It's impossible for us to induce the retailer to order the system optimal quantity. Okay, the proof is here. Suppose R is 0. Okay, suppose R is 0, you can see again this term goes away. When R is 0, this term goes away, and your P will cancel each other. You will get W minus P plus P minus C, that's W minus C. You are asking W minus C to be 0, and that's impossible because the cost must be less than your wholesale price. And then, if R is 0, what's going to happen? I mean capital R. In that case, what you will get is this term will be cancelled, and you still have R times F of QT star, and then the first part does not change. Okay. You have this, and then what you need to do is to plug in capital F of QT star. You know that's going to be P minus C over P, something here. Okay, after you do this plug-in, you're going to see that again, we are asking W to be equal to C, which is again impossible. So this derivation tells us that if we do not allow return, if we apply only a wholesale contract, this will be system suboptimal. Okay, so now let's consider some intermediate case. Let's consider, for example, 4 returns with partial credits. And here we're going to show you that this will work. 4 returns with partial credits. So suppose capital R is 1 for return. Then we can have this condition hold if and only if we have this equality. If and only if W and R satisfies this equality. Okay? So that's something we need. Then we want to know whether this is possible or not. So the second condition, the second statement here is that given any problem instance, there is a pair of R and W such that we have this regularity condition. Your return quantity is smaller than your W. These W and R can always be found to satisfy the above equation, which means when we apply 4 return with partial credits, we can achieve trinomial coordination. We can make the retailer order QT star. Okay, so first, when R is 1, we know this part will goes away, and the first part would be immediate, because when this guy disappear, then what we need is W to be equal to the other thing. Okay, so that's how we get the first part. And then if we do something to this equation, we can express R as a function of P, C, and W. Okay, then as we know W is less than P, this part would be less than W. Okay, that's something you may show. And also because C is less than W, so this term would be greater than 1. Eventually you can see we need R to be calculated in this way, and this thing would be greater than 0 and less than W, which means the return credit R is just something feasible. So if we allow 4 returns with partial credit, as long as we design the wholesale price and the return credits in a reasonable way, satisfying this equality, then we can make our system optimal. We can induce the retailer to order the system optimal quantity. In this case, we say the return contract coordinates this system. Okay? So, under a full return contract, channel coordination requires something we just proved. And if you want, you may do some arrangements, you may take this part in a different format, and after some arithmetics, you will show W must be something like this. It will be C plus some ratio of R, okay? And you will immediately see W and R are somewhat proportional. When W increases, R must also increases, or somehow less intuitive. Suppose I want to coordinate our channel, and suppose I want to make the wholesale price higher. Okay? When I make the wholesale price higher, the retailer has the incentive to order fewer products and to maintain the order quantity to be system optimal. I need to give her some more incentive to higher the order quantity, and that must be the increase of R. Okay, that's the intuition here. We know that the expected system profit would be maximized with a coordinating contract, and that means the pie is maximized. And then we may need to ask whether this pie is split fairly under a coordinating contract. Okay? Why do we need to ask that? It's because if the allocation is not fair, then at least one of these two parties will refuse to sign a coordinating contract. Okay? Think in this way. Originally, under a wholesale price contract, each of them can earn some money. Now we apply a coordinating return contract. We know together they earn more money. But how do we know each of them earn more money? If that's true, they would be willing to sign the coordinating contract. Everyone is happy. But if that's not true, one of them actually gets worse off under a coordinating contract, then that's not going to be practical. Okay? So we want to ask whether the profit splitting is fair. But we know fair can mean very differently under different scenarios. For example, the manufacturer and the retailer, their size may just be different. So fairness does not mean one half, one half. Or if you are saying proportional to their size, then it may be something that's hard to measure. And sometimes whether it is fair depends on the bargaining powers of these two parties. So in general, here we do not try to define what is fair, and we want the pie can be split arbitrarily. That means we hope that our contract has the following property. There's a pie. Okay, I want to split this pie, 30% of this pie to the manufacturer. I hope that's possible. I want to split 20% to the manufacturer. I hope that's possible. No matter what's the percentage I want to give to the manufacturer, I want that to be possible. Okay, that's something we called arbitrary profit splitting. Okay, arbitrary profit splitting. I want the pie can be cut in any way I like. Okay, so let's see. Let's start to analyze this problem. In one limiting case, even though we know that's not possible, but the limiting idea will help. Suppose the wholesale price is C. Suppose the wholesale price is C, then we know R must be 0. Okay? What's more important is that we can see in this case, the manufacturer is going to earn nothing, and the retailer will take whole the pie. Why the manufacturer can earn nothing? It's because the wholesale price is nothing but C. Okay? When I sell one item to you, I get nothing. And also there will be no return. Okay? So the manufacturer has no way to earn any money, and all those profits are in the retailer's pocket. On the other hand, suppose we set a very high wholesale price, which is equal to the retail price. In that case, to make coordination possible, if W is P, we can show that R must also be P. Okay? In this case, we can see that the retailer earns nothing. Why? Because the wholesale price is so large. So even if you sell one item to the consumer, you earn nothing. Okay? And also, eventually, you are allowed to return anything you buy at the original price. So that means you are, in some sense, doing nothing. Okay? And the whole pie is taken by the manufacturer. So we have seen two special cases. In one special case, the manufacturer gets nothing. In the second special case, the retailer gets nothing. Okay, so there are at least two different ways to split the total profit. How about those intermediate cases? So here we need to visualize all the possible situations. Okay, so let's draw some graphs. First, let's do this. Okay, I'm going to put R at the x-axis and W at the y-axis. Okay, I know the return credits cannot be greater than P, and also the wholesale price must be between P and the cost C. Okay? Okay, so now something I know from the previous slides is that one possible alternative is to offer a contract that the wholesale price is so low and the return credit is zero. That's one extreme. Another extreme is here. I'm offering a very high wholesale price, but I need to give you a very high return credit. Okay? And you know the set of coordinating contracts lies in this line segment. Okay? Is everything on this line segment can coordinate the system if we assume full return. Okay, there are something more we know. At the first extreme, pi m is 0, and at the second extreme, pi m is pi t. And what we are asking is, what happened to those intermediate cases? So let's draw another figure. Here I'm going to draw pi m. Okay, so the x-axis would be W, the wholesale price, and it must be within C and P. Okay, for pi m, I know something. First, it can never be greater than pi t star, right? And again, and also, when the wholesale price is nothing but C, I know the manufacturer gets nothing. But when the wholesale price is so high as P, I know it can get everything. Okay, now is the interesting part. I know the manufacturer will start to earn something more when the wholesale price becomes larger. Why do I know that? Because somehow the manufacturer's profit function, this thing, is continuous on W and R, W and small r. And that means the function goes from this first point to the second point, must be something continuous like this. Okay? And in fact, what we may show is that this line would not be something like this. It will be actually an increasing, monotonely increasing function. Okay? And that will directly tells us that for the retailer's profit, as it must sum to pi t star, it will be a decreasing line, goes from pi t star to 0. Okay? And what's the implication here is that actually there is always a way to achieve arbitrary profit splitting. Okay? you may ask for any number, for example 0.3, 0.5, and there is always a way to achieve that particular split. You can say that I want to give 30% to the manufacturer. That can be done, right? Because all you need to do is to say, okay, 30% is here, then I need to set the wholesale price here. If you want 80%, okay, 80% is here. Okay, all I need to do is to set the wholesale price here. Okay, everything can be done as you wish. Okay, so let's conclude what we did. Because pi m is continuous in W and R, pi m star must gradually go up from 0 to pi t star as W increases, or you may say as R increases. Okay, the key here is gradually or continuously, and this is why we may guarantee arbitrary probability splitting. So that's something good. That's something important here. We actually do not need to show pi m star is non-increasing in W. Okay, it's not needed. All we need is continuity. Also, pi r star must also gradually go down as W increases or as R increases. So we say we can achieve arbitrary profit splitting. And that means there is a way to achieve the coordinating contract. Everyone would agree with that. So we know the return contract can be coordinating. And here coordinating means inducing the retailer to choose the system optimal quantity. And that means the pi is maximized. And now we also know that this can be win-win. Why? We will first make the pi as large as possible. And then we can split the pie in any way we want. That means we will always be able to make both firms happy, and they will be able to agree the contract. So we say the two players will agree on the contract. And also at the same time, you may show that consumers are also benefit from the channel coordination. Why? The price, the retail price is fixed there. Under channel coordination, the wholesale price, under channel coordination, the order quantity will increase, will be higher than the case with only a wholesale price contract. So more consumer can buy this product. Everyone is happy. Firms are happy, and the consumers are also happy. Okay, if you do some more study here, you will see that there are some other coordinating contracts, and not all of them are win-win. So the win-win condition here, or arbitrary profit splitting, is important for coordinating contract, because if we want the coordinating contract to be feasible or to be practical, we need to have this win-win condition. Okay, finally some remarks. We only introduced the main idea of this paper. Actually, if you remind yourself, if you think about what we have done, we analyzed return contracts. We analyzed the full return with partial credit. How about partial return with full credits? That's something we do not touch, right? So there are still a lot of things that you may find in the paper. For example, in the paper you will see we can handle salvage values and shortage costs. Even if we have this possible with these things, we can still have the previous results. Also, the monotonicity of the manufacturers and retailers' expected profit have been proved in the paper. Here I would say that this part is not the most important thing, right? But it's interesting to know this is true, and also this intuitive, right? And finally, in the paper, he discussed something related to the multiple retailer case. Okay, he would argue that the contract would be possible to coordinate one retailer, but when there are multiple retailers, things may be different. Okay, I won't study those parts for you, and I won't explain those parts to you. You are encouraged to read the paper by yourself. So to the minimum level, you just need to know what I have covered in these lectures. But if you are able to read the paper, then you are going to get more. In always the case that the more effort you put in one thing, you're going to earn more. Lastly, channel coordination or supply chain coordination. This was a hot topic about 20 to 30 years ago, but actually it is not so hot in these days. Anyway, in the past times, people have tried to characterize, to find so many different ways to coordinate a channel or a supply chain. Some keywords I listed here are including on two-part tariffs. Okay. Besides the wholesale price, you are also allowed to charge or to give a fixed payment. That's two-part tariffs. We're going to see that later in this semester. There are also something like quantity flexible, revenue sharing options. If you are interested in that, you will be able to find them easily online or in any supply chain textbook. Okay, so I will stop here. The whole thing we want to tell you is that decentralization causes some problems. For example, incentive misalignment. For example, double marginalization. And what do we want to do? We want to design some mechanism to solve the incentive issue. We want to be able to find a way to induce people to make a more efficient or even the system optimal decision. That's the key idea here. And we show that a return contract is one way that will work in a particular situation we consider here. Okay, that's the end of this lecture. Thank you.